Okay, so this is the outline for chapter 24. So we first will introduce the last most important variable for the electrostatics, which is called electric potential, or sometimes in the circuit theory we will call it voltage. So sometimes I may just call it voltage. So you need to I hope you can understand. Or it is actually, yeah, somehow it is not the same as electric potential, but sometimes it is the same thing. So okay, so we'll introduce electric potential first, and then we'll introduce equal potential surfaces and the electric field. So the equal potential surfaces is related to the electric field lines, so it's somehow perpendicular to the electric field lines. And then we will talk about the potential. So due to different structure, so just like what we did in previous chapters, we will try to calculate the potential due to different structure. Like a charged particle is the easiest one, and then with by the electric dipole, and then continuous distribution, and then calculate the field the E field from the potential. So there are some relationship between the electric field and the potential. And so sometimes the potential is a way to let you calculate the E field. So if you find the method in chapter 22 is difficult, and also it might not be easy to apply the Gauss law, then you may try to come up with the potential first, and then with some calculation, then we can transfer the potential into the E field. Okay, so so that's what we'll learn in this chapter. Okay, so then the remaining stuff is electric potential energy, and and potential of a charge isolated conductor. Okay. So first here we will introduce what is electric potential. So so this is the definition. Electric potential. We usually will use V to specify the electric potential. Uh, so so it is like the definition. This is a definition. So the electric potential is like the work done by the E field to put it from infinitely far away to the point P we concern. Okay, so usually we will define the electric potential at infinitely far away to be zero. Okay, so so in the mechanic class or physics one, you will have some similar formula like the work done is the negative of a potential. So we have a equation like a V equals capital U over Q naught. Okay, so here we also assume that this charge is a positive test charge. Okay, so so this is pretty much like this. So you can, so you can imagine you need to spend some force to put the charge close to a positive charge. And so this is one very important equation. We may still need to use it later, which is the electric potential equals the charges multiplied by the electric potential. So this is the potential energy, potential energy. This is the electric potential. Electric potential. Okay. Yeah. So we have some so simple formula like Yeah, so if we need to move a charge from, this is the initial electric potential to the final electric potential, then we need to change the potential energy. Need to change the potential energy, just like what you have learned in mechanics. So, for example, if you have a mass here, uh, we have a mass, and then suppose it is on the floor, so this is h equals 0. If you need to move it higher, for example, to h, we need to move it up, then the potential difference will be mgh minus 0. So this is the initial potential energy. This is the final potential energy, will be mgh, something similar to this one. Yeah, so here W equals to negative delta U. So you have a negative sign here. And then here we consider the conservation of energy. So if we assume there is no energy loss inside the system, then we will have the conservation of energy, which means that the total mechanical energy doesn't change. So the total mechanical energy will be K initial plus U initial. So the kinetic energy plus the potential energy will be the same as the kinetic energy at the final stage plus the potential energy as the final stage. So yeah, so you can just move over the terms, then you will get, let's say, get Kf minus Ki will be negative Uf minus Ui, something like this. So this one is delta K, this one is delta U. So we have delta K equals negative delta U. So we have a delta K equals negative delta U, and delta U is nothing but Q delta V. So we have a expression like this. Okay, so here if we would like to apply the forces to the maybe the particle, then there will be work done on it, then yeah, the kinetic energy will change. Okay, so let's see a simple sample problem. Okay, so it says electrons are continuously being knocked out by air molecule in the atmosphere by cosmic ray. Okay, okay, so air molecule 就是空气分子 in the atmosphere 是大气层 and cosmic ray is 宇宙射线 okay, which is some sort of a high energy particle. So coming in from the space, once released, each electron experience an electrostatic force F due to the electric field E that is produced in the atmosphere by charged particle already on Earth. So here near the Earth's surface, the electric field has a magnitude E equals this magnitude and is directly downward. So we have the E field pointing downward here. And what is the change delta U in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance d? Okay, so we have a distance, need to move upward. So it asks you what is the delta U, what is the change of the potential. Through the potential change, does the electron move? So what potential change does the electron move? Okay, so here I think in mechanical class or physics 1, you know, the work done should be F dot D. So D is the displacement. So it moved from bottom to top. So the has this direction pointing upward. And then the F is also pointing upward because E is pointing downward. E is a negative charge. So when a negative charge plays in a electric field, the force will be opposite, will have an opposite direction with the E field. So F is pointing upward. Here, F and D points to the same direction. So we have a positive value, F times D. So here F is actually Q, which is actually Q times E, Q times E. From the chapter 22, we know F equals QE and then times D. Okay, so we can plug in the values. Q is the absolute value of E, which is 1.6 times 10 to minus 19. Okay, so times E is 150 times D. D is 520 meter. Okay, so this value is 1.2 times 10 to negative 12, and then joule. Okay, so the SI unit for the work for the energy is joule. Okay, so this is the work done by the E field. This is the work done by the E field. Actually, not the answer to this question. So maybe we don't use the box. Okay, so this is the work done by the E field. And then the potential change will be negative W. So which is nothing but negative 1.2 times 10 to a negative 14 joule. So this is the potential change. Okay, so next we can also apply, we can also calculate the potential change, because it asks you the potential change. So the potential change is nothing but delta U, no negative, delta U over Q. So delta U over Q is maybe you can just put an absolute value here would be better. Okay, so we have delta U is negative 1.2 times 10 to minus 14, and then here we have negative 1.6 times 10 to minus 19. So delta V will be 4.5 times 10 to the 4th volt. Or you can write it as 45 kilovolt. 45 kilovolt. Okay, I think this sample problem is quite simple. So let's move on to the next point. So here we will introduce the equipotential surfaces and the electric field. So here it says the adjacent points that have the same electric potential form an equipotential surface. Yeah, so which can be either an imaginary surface or a real physical surface. So here it says shows a family of equipotential surface associated with the E field due to some distribution of charges. And it says the work done, so this is the highlight point, the work done by the E field on a charged particle as the particle move from one end to the other end of path 1 and 2 is 0. So let's see what it means. So this is path 1. path 1 is all the way on the equipotential surface V1. So it means that this is a surface and then have the potential V1, electric potential V1. So this is a equipotential surface. This is another one, V2, V3, and V4, so on and so forth. So yeah, so here path 1 is all the way on the V1. So if we have a charge move from this point following this path to here, there will be no work done on the charge. So the work done by the electric field on a charged particle for path 1 is 0. And path 2, let's see, path 2 is here. So path 2 is here. So the starting point and the end point of path 3 are all on V3 surface. However, the path itself is not all the way on the V3. However, when the charge goes from this point along with this path and then go to the end point back to V3 surface, then the work done is still 0 for this path. Of course, from the E field. So yeah, so actually the work done is only related to the starting point and the end point, doesn't related to the path it goes. So if the path is starting from here and then go for many loops and then go back to here, then yeah, still the work done will be 0. And the work done as the charged particle move from one end to the other end of path 3 and 4 is not 0. So here, this is path 3. So it goes from V1 potential surface to V2 potential surface. So yeah, so of course there will be a potential difference. So delta V3 will be V2 minus V1 and is not equal to 0. So here we know the delta U equals Q times delta V. Okay, so as delta V is not 0 and delta U is not 0 also. So as the work done. So this is not 0, this is not 0 also, this is not 0 also. And for path 4, where is path 4? Path 4 is from here. Sorry. Path 4 is here. So it starts from V1 going a bit over and then go back to V2. So here, delta V4 is actually V2 minus V1, which is not 0. Okay, so in this case, the work done for it is not 0 either. Okay, so this is path 3 and path 4 connect the same pair of equal potential circuits. This is path 3. Yeah. So yeah. So it actually means this one and this one are actually the same, which means that the work done when the charge go along path 3 and path 4 will actually the same. They are not 0 and with the same, actually the same value. Okay, so here we try to consider the potential difference in a more rigorous way. So here it try to define electric potential difference between 2 points as a line integral. So this one is so-called line integral. Okay, so yeah. So here, let's try to look at this figure. Okay, so here in this figure, first we can observe The blue arrows are all the E field. So the E field. Okay. So yeah, it is not uniform generally. So you may consider, yeah. So this is the E field line. So yeah, so at this point, E field is pointing that way. At this point, E field is pointing this way. And so as this one, this is the E field at this point. Okay. So here we try to define a path, which might be an imaginary path. So this is the initial point, this is the final point. And of course, this path is not necessary to be a straight line. It might be a curved line. So in this case, we would like to do this line integral. So how to calculate the line integral? We try to separate this line into many small segments. So every small segment, we can regard it as a straight line. And then, of course, we go from I to F. So, so the ds is all the way the tangent line to this path. ds is the tangent line to the path. And of course, follow the direction from I to F. Okay, so in this case, if we would like to calculate the small e dot ds, so we can have ds pointing to this direction, and then e is pointing to this direction. So we can come up with e dot ds for every small segment, and then we try to add all of them together. Then it will be we add all the part together. Maybe call it k. We add all of them together, so that it will be like the surface, the line integral E dot ds. And as you know, the dot for the dot product, after dotting to vector, it become a scalar. So we just add many scalars together. So in that case, the potential is also a scalar. The potential is also a scalar, and also the potential difference is a scalar. And I think, yeah, so I think here we do not include the SI unit for the potential yet. So the potential, the SI unit for V, maybe I write it here. SI unit for V is actually V. Actually V. So it is a short form for the volt. Volt. So actually, I found many students cannot distinguish voltage and volt. Volt is the SI unit. Voltage is in Chinese stanya, so it is similar to call it electric potential or potential difference, voltage difference, potential electric potential are quite similar thing. Yeah. And volt is the SI unit, but yeah, usually I heard many students say 3 voltage, which is not correct. And actually, they are not mentioning V voltage, but V volt. Okay, so yeah, so this is the mathematical meaning for this line integral. So calculating this line integral and then take a minus I will be the potential difference. So sometimes we will simply write it as V equals to negative of this line integral E dot ds from I to F. It says if we choose Vi to be 0, then then Vf minus Vi is nothing but the V will be the voltage difference or the potential difference. So in a uniform field of magnitude E, the change in potential is this one. So sometimes we'll use this one, and maybe in high school physics, uh, it introduce this one because it doesn't involve any calculus. It will be acceptable for high school student. So we have a delta V equals negative E times delta X. Delta X is we assume that E is parallel to the movement or the displacement. So we have a V, delta V equals negative E times delta X. Okay, so as much as the SI unit for V is also V, and if we use this equation, we can see that this is the SI unit here is V, the SI unit for delta X is meter. So another SI unit for E is volt per meter. And of course, in chapter 22, we know the SI unit for E is Newton per coulomb. So actually they are the same. Both of them are correct. So in the quiz or exam, you can either using one. Okay, so here we have delta V equals negative E times delta X. Okay, so let's have a 10 minutes break, and we will continue.